All right, we're back. We're still in lockdown, but we've got plenty of things to discuss. So today we're going to discuss life and the periodic table. So we know from chemistry that there's fundamental elements that make up all the compounds we see around us. They're listed in the periodic table: hydrogen, helium, lithium, on and on we go. What is the connection between, what does the periodic table have to do with life?
Okay, so I've got my handy copy here. We discuss this in A Fortunate Universe. So yeah, let's take a look at the picture of what we have. Right, we know that quick summary of elements in the universe. The universe was born hydrogen and helium, teeny bit lithium.
Mm-hmm.
That gas collapses into stars. Those stars undergo nuclear fusion at their cores. They create heavier elements. Those elements get spat out. Eventually you get to massive stars and the deaths of neutron stars, etc., where you get really extreme conditions and you can build up heavier and heavier elements.
Mm-hmm.
So what we're talking about when we talk about an element, of course, is that we're talking about, let's just deal with individual atoms. You have a nucleus,
mm-hmm.
okay? You have electrons.
Mm-hmm.
Your nucleus is comprised of two kinds of particles,
mm-hmm.
right? Protons and neutrons. Now, they're not fundamental,
yep.
right? Because they can be broken down into quarks, but that's not part of this story, really. You've got protons and neutrons. And what we know is that you can build these nuclei out of mixes of protons and neutrons, but not arbitrary mixes.
Mm-hmm.
Right? So you can put protons and neutrons in there, but I can't have, one proton and 5,000 neutrons because the
mm-hmm.
thing is unstable, right?
Yep.
So, and of course, when we talk about elements, what we're really talking about is the number of protons in the nucleus. The protons are charged, positively charged, so they set the charge on the nucleus. Then the electrons join, and you have the same number of electrons as protons when you have a neutral atom.
Yep.
Okay. And then you get this entire thing of whatever the outer electron is doing, the outer electrons, that is how an atom talks to another atom.
Yeah.
Right? So if you want two atoms to join together into a molecule, then it's the physics of the outer electron is chemistry, as they say.
As we say. That's all I was going to say.
Yeah. And of course, what we have is that you take atoms, you join them together, two hydrogens and oxygen, give water. Water is thought to be one of those essential things for life. Okay. Mm-hmm. So essentially, at some level, the chemical elements are our building blocks.
Mm-hmm.
They are our Lego. And I actually, as a complete aside, I heard that the Lego Corporation said it's completely incorrect to say Legos.
Yes. They've tweeted about it. I've looked this up. Yeah.
They are Lego bricks, not Legos. Anyway.
Good.
So quite clearly, we are governed by biochemistry, which is based upon our molecules. And it turns out that our molecules do what they do through their shapes, right? Mm-hmm. So, your water molecule is oxygen, two hydrogens. Mm-hmm. There's a particular shape to that molecule. The way it interacts with other things depends upon its shape, blah, blah, blah. But let's go and look at, firstly, the basic chemical toolkit. What do we have, mm-hmm. right? So we know that we have effectively 92 natural elements.
Yep.
Right? Hydrogen out to uranium.
Yep.
That's the most massive natural element. And the only difference between one element and the other element, if you just drew a straight line, is the number of protons in the nucleus.
Yeah.
So hydrogen has 1, helium has 2, lithium has 3, all the way up to uranium, which has 92 protons. Is that correct?
They must.
Right. Woof. That's good. Okay.
You can see the da is where actually we haven't memorized that much of the periodic table.
Yeah.
I mean, beryllium, boron, carbon, I'm done.
Nitrogen, oxygen.
No, I think it's oxygen, nitrogen. No.
Nitrogen.
This is the point. Yeah, it is nitrogen. Yes, good. 7, 8, neon, something else.
Yeah. Anyway, okay. So what we've done there is we've drawn this picture where we've added 1 to each element, and you get this thing called the periodic table. Hydrogen, helium, lithium, beryllium, carbon, nitrogen, oxygen, blah, blah, blah. And you build up this picture. But that's not the full story, of course, right? Because that is really talking about the number of protons in the nucleus. I can actually expand this out into 2 dimensions.
Mm-hmm.
I can have the number of protons. So I have a, 1 column for each of my elements.
Mm-hmm.
But I can also talk about the number of neutrons in each element.
Yep.
Okay? So let's take a simple example. Let's take hydrogen.
Mm-hmm.
Okay. So hydrogen has a proton, but that's not the only form of nucleus that a hydrogen atom can take, because you can take a proton and you can stick a neutron to get to it. And so you have still got hydrogen, but this case here, this is known as deuterium rather than just normal hydrogen.
Yep.
And what we have, of course, is deuterium is an isotope of carbon.
Yep.
I can even add another neutron, and I can create tritium.
Mm-hmm.
Okay. Again, another isotope of hydrogen. And I can't do anything else. I don't think you can go any higher than tritium.
No, I don't think so. Can I just point out, just there behind me is my grandfather's PhD thesis, where he measured levels of tritium in underground water.
Oh, yeah.
To measure, because atomic bombs affect the atmosphere more than the water, you can sort of date how old water is from the amount of tritium in it, because it's got anyway, it was something. So, yeah. Just to point that out, it's right there. It's one of my prized possessions.
Excellent. Now, so that's kind of interesting, right? Is that I can't keep adding neutrons and getting more and more massive nuclei of hydrogen, because they just don't stick together anymore.
Yeah.
Right.
The way I think of this, which is probably not correct, but quantum mechanically, a free neutron itself is unstable. So you just have a neutron just in empty space. It's got about 15 minutes before it will undergo a decay into a proton, and I've got to get this right, a proton, an electron, so that the whole thing is neutral, and then an electron anti-electron neutrino. And so the way I remember this fact, I don't know if this is correct, but if you have too many, so a neutron can be stable if it's connected to some protons. If you have too many neutrons, it's almost like having a neutron in empty space. They're sort of a neutron hanging around with other neutrons isn't enough to make it stable. It's got to hang around with that proton. So too many neutrons is bad, because it's just like just hanging around with protons, being a neutron in empty space. Yeah. That's how I remember it. I don't know if that's correct.
It's part of the story, but not the complete story.
Sure.
Okay. You just can't you can't build a stable nucleus that has just too many neutrons in it. Similarly, you can't build a stable nucleus that has too few neutrons in it, and we'll come to that in a moment, right?
Yes.
So you can go to other elements. Let's take carbon.
Yep.
Right. So carbon has 6 protons. Mm-hmm. Yeah, but we'll assume that our viewer is a physicist and so won't actually know these numbers.
Yeah.
And the typical kind of carbon nucleus that people talk about has 6 neutrons. So you talk about carbon-12, which is 6 protons, 6 neutrons. But you can add a few more neutrons and take a few neutrons away and still end up with a nucleus of carbon.
Yeah.
Okay? So we could do that to all of the elements. So remember what we've done now is we've made this 2-dimensional plot of basically number of protons, total number of things in the nucleus, right? And we've got this distribution over there, over this space.
Yep.
Okay. And somewhere in there is a dot which says carbon-12.
Yep.
And then there's a couple more isotopes of carbon. But eventually we get to the point where you can't stick any more neutrons on. Okay? And get to the point this way where you can't take any neutrons away.
Mm-hmm.
Okay? What you've got there is a range of the isotopes of carbon and all the other elements. So if you imagine this picture, you got number the element here, number of you're gonna put a picture in the.
I was just thinking. I'll put a picture up. Yeah.
Put a picture. So what we have is essentially, if you look at it from above, it's called the valley of stability, right? Mm-hmm. So we have essentially this line that runs down the middle, where we have what we call the stable elements, right? The stable isotopes of elements. Mm-hmm. Okay. Then we go off into the isotopes, and either side, one or two of the isotopes might be stable. Mm-hmm. But then as you move further and further away, they become less and less stable. So they become subject to basically nuclear decays, as you mentioned there, where a neutron decays into something else. Yep. And you get a change from one element to another. So you can imagine that we've got this thin band of stable elements, and either side there are the radioactive isotopes that can decay into something else. Mm-hmm. And of course, when we look at what we're made of essentially the stable isotopes.
Yes.
It sort of makes sense, right? Otherwise, things would decay away. So, you have the stable elements. So one of the interesting questions is where does this valley of stability come from?
Yeah.
Right? So the valley of stability is a mixture of the forces at work inside the nucleus of an atom. And you have three of the four fundamental forces doing their things there. Mm-hmm. You have the strong force holding things together. You have the electromagnetic force wanting to force the positive protons apart. Mm-hmm. And you have the weak force, which causes weak decays, right? Mm-hmm. And
what you don't have is gravity. Gravity doesn't make any.
Gravity doesn't matter inside nuclei, right? So in your stable nuclei, you must have this situation whereby the strong force and the electromagnetic force have basically decided that they've come to some sort of arrangement and things have balanced, right? And the neutrons which are in there can't undergo their decay because they're so tightly bound together that you can't energetically turn one into a proton, right? So you get a stable element. So we have this valley of stability, which is really important for life, right? If we didn't have this stability, so if you imagine we adjusted the forces, right? So we adjusted the electromagnetic force and the strong force, which meant that the weak force could start to turn neutrons into protons and even protons into neutrons inside the atom, inside the nucleus. Mm-hmm. You can erase the valley of stability.
Yeah.
What I mean by that is that every nucleus in the universe becomes radioactive. It will decay on some time scale. Yeah. Now, that would be bad for life, right? Because if you want to create, imagine the initial stages of life, where you create some self-replicating molecules, mm-hmm. you want those molecules to last long enough such they can replicate before a nucleus in one of them decays and it turns into a different element.
Yeah.
Right?
So life is fundamentally based on information.
Yes.
So something in there's got to record the information. You can't have, I write down something on a piece of paper and overnight the message starts changing because the letters decay into other letters. That would be a bad outcome.
That's right. So as you mentioned, the information written into DNA, that is written by the nucleotides. They are made up of atoms joined together in certain ways. And you don't want your carbon atoms turning into nitrogen atoms, right? Because that changes the entire molecular structure.
Yeah.
So we need that valley of stability. So there is a limit on the relative ratios of the strong force, the weak force, and the electromagnetic force that gives you the valley of stability. You could erase the valley and everything could be radioactive. That would be bad.
Yeah. So just to give a rough idea, I think the number's something like, as a simple example of just change one constant, if you take the strength of the strong force and just turn it to about half of what it is, carbon and anything bigger than carbon is unstable. There's actually no isotopes at all. There's not even the radioactive bit of the stability. It just, the valley is very short, and everything bigger than that is gone. So that's a very extreme change, of course. In as we think about turning it back a little bit less, you'll slowly erase more of the valley.
Yeah. So erasing the valley is bad, but what if we do the opposite? What if we broaden the valley? What if we start to make more and more isotopes and make them more and more stable? What if I could create a hydrogen atom with 10 neutrons?
Yeah.
Right? Now, you might say, well, okay, yeah, that just gives you more elements to play with. But there's a critical issue here, right? Remember that if we take a water molecule, right? A water molecule, as you've said, is a oxygen with two hydrogens hanging off it, and it has a particular angle, I think 105 degrees, that number.
Yeah, it's about that.
Yeah, that's the angle that the hydrogen atoms are with regards to the oxygen atom. Where does that angle come from? Well, that is a combination of the forces involved, which are electromagnetic. That's what gives you your molecular shape.
Yeah.
And the masses of each of the atoms. So if I create a water molecule and instead of hydrogen, I use deuterium, right? I get a different angle. Now, it's not that different because remember, all we've done is added one neutron here, one neutron here. The oxygen is still the dominant thing. And I looked into this a little bit. I think you can drink heavy water, which is what this is called, right? Because you've now got deuterium rather than hydrogen. Okay.
I think it kills rats, doesn't it?
I think it's mildly toxic. Like all good experiments, when it kills rats, you basically put them in a bucket of it.
You say we'd better not give this to humans. Yeah.
Yeah, but I think it's mildly toxic.
Yeah. It's don't is the short story.
Yeah. So what happens is that because the angles of the molecule are slightly different, it means it interacts with all the other molecules slightly differently.
Yeah.
Okay? Now imagine that instead of that hydrogen, deuterium and tritium, I then add all the others. Let's now make water with 10 neutrons instead of no neutrons. If you now take those big hydrogen atoms, the outer electron still does what the outer electron does. It still says, I'm hydrogen, I will join to my oxygen to make water. But you completely change the angle, which means that the chemical reactions that molecule has with other molecules are changed, right? And that just gets worse when you end up with bigger, more complicated molecules. The most important thing for a protein, right? A protein is one of the fundamental building blocks in your body, is its shape. What shape is that protein molecule?
Yeah.
And that shape is set by the electromagnetic force and the masses of each of the atoms involved or the nuclei involved. And if you are trying to have a biochemical reaction where this molecule does something with this molecule, they sort of like fit together. If you have an entire, range of potential carbon atoms you could use, and oxygen atoms and nitrogen atoms, that means that two molecules, even though they are made of the same atoms, may have radically different shapes. So they might chemically be the same thing, but how they interact with the rest of living material might be pretty different. So in terms of the valley of stability, you definitely don't want to erase it, but you also don't want it to be too broad either, because we'd have just too many potential isotopes to work with. And we've ended up in a universe that gives us a narrow valley with essentially one stable isotope per element.
Per element.
Yeah.
it's interesting to think about the difference between those two cases, though, because this is something that we need to keep stressing with this whole fine-tuning thing. In one instance, you know, erasing the valley, the universe gets a whole lot simpler. Okay, half the value of the strong force, half the strength of the strong force, and you can throw all your carbon chemistry textbooks away. There's no carbon anymore. And so what happens is, if you compare that universe to our universe, that universe is really simple, right? There's hardly any chemical reactions. And so when we say life's going to have trouble over there, it's because things are too simple. You can't build up the complexity you need. Going the other way is that the other case, though. Now things are sort of too complicated. Now your chemistry textbook is really much more complicated. So, for example, you'd have to specify. We talk about a reaction like carbon plus oxygen makes this. You'd have to then specify which isotope you were talking about when you did each of these reactions, and all that would just make all the chemistry much more complicated. Could life still form? Well, it could if it just found enough of a pure sample of the right kinds of the elements, and it could still in principle do what we're doing. That would still be possible, but you've just thrown in this curveball, this complicating factor of now life's got an extra hurdle to jump over. You can't just rely on the fact that if you get some carbon and then you'll use carbon to make this and then all that'll happen. Now you've got different types of carbon floating around. You've got to make sure your samples are all pure when you try and build. So that's a more complicated case. It seems like whatever's happening in that universe, it's going to be harder to make life there than it is here. It's obviously not impossible, but given that we don't know the process by which it happened here, will life happen over there? It's kind of hard to tell.
But it is very interesting that said that we find ourselves in a universe with a narrow value of stability.
Yeah, it's really easy. Like I said, I'll throw the picture up again now. So in the picture, I can just grab one. There's a nice one on Wikipedia actually. That there's a whole bunch of them you can get. It's got this set of graphs. There's all the radioactive ones, and then there's the ones that are stable, and it's just basically a single line. And it could have easily been no line. It could have easily been a broad range of stable ones, but it's just basically a single line. That's really, really interesting. You gotta get your tuning dials just right if you want that situation.